All right, welcome to The Explainer. Today, we're tackling a massive crisis right at the beating heart of modern artificial intelligence. We're talking huge energy drains, brutal memory walls, and this creeping computational drift that is just severely holding back infinite context AI. If you've been tracking the sheer, ridiculous thermodynamic cost of running large language models lately, you know we are hitting a very real, very hard physical limit. But here's the wild part. What if the root cause isn't actually a hardware flaw at all, but a foundational mathematical glitch? 74 times. Let that sink in for a second. We're not talking about some tiny software tweak here. The research we're unpacking today demonstrates a mind-blowing 74x reduction in energy per scoring operation for AI inference. Think about the scale of that. We are literally talking about dropping the metabolic floor from standard power-hungry levels down to a microscopic 0.05 picojoules. This represents a total revolutionary shift in our hardware limits. It completely redefines how we process information at the absolute most basic physical level. Okay, let's dive into this, because this is where our explainer turns into this fascinating historical detective story. The core argument here is that the massive energy drain and those memory walls we see in AI today, they aren't actually modern problems. Rather, they're symptoms of a 400-year-old mathematical fracture. It's a fundamental glitch in how we calculate scale and rotation, something we basically just blindly accepted for centuries without really questioning its true metabolic cost. To really understand this, we actually have to trace the root cause all the way back to 1614. That's when John Napier gave us continuous logarithms. Now, Napier's system was revolutionary for sure. It gave us the base for log scale, but it had a fatal flaw. It relied on a continuous point line paradigm that lacks any sort of physical boundary. Fast forward through the digital revolution, think of the 1999 Napster strike that totally liquidated physical music media, and that brings us right to 2026. Modern AI has hit what researchers are calling the Trig Wall. Basically, Napier's legacy of continuous math has directly caused modern AI's approximation drift and its massive thermodynamic costs.
Let's break this down with a visual. Imagine legacy continuous math as this frictionless, endless ramp. You can slide down it infinitely, right? But you never actually hit a precise, fixed bottom. You have to constantly use energy-heavy approximations just to figure out where you even are. In stark contrast, the Higgs Universali framework, or HU math, introduces a discrete model. And Higgsity essentially means thisness, or absolute uniqueness. So this framework is like a physical staircase with a solid floor. In a true computational republic, sovereignty is resolution. You absolutely need a physical boundary, a discrete step, to anchor your computation so it doesn't drift. So here's why that endless ramp is a huge problem and creates this Trig Wall bottleneck. To figure out relationships between data points, current AI relies on complex, irrational math, things like sines and cosines. Calculating these endless, transcendental angles is unbelievably metabolically expensive. Plus, it creates what we call approximation drift. Over time, it literally causes the AI to hallucinate. Instead of preserving that discrete hecticity, that pristine forensic uniqueness of the data, it just smears it all into continuous, undifferentiated gunk.
And this brilliantly illustrates the hero of our story, the HU logarithmic equation. It perfectly captures this vital shift from Euclidean spatial approximation to precise, discrete algebraic steps. It's the definitive logarithmic answer to that 400-year Naperian fracture we've been stuck with. Let's deconstruct exactly how this elegant piece of math restores a real physical metabolic boundary to our computations. Okay, here's exactly how the equation works under the hood. First up, we've got d, that's our logarithmic base, often referred to as the lens. Next, there's d sub n. This is absolutely crucial. It's the finite remaining area at step n, powerfully known as the quark. And finally, n++. That's the discrete integer nesting level, the exact trackable step, the hacka-huggy. By using this equation, you aren't calculating some endless irrational angle anymore. You are simply counting discrete bounded steps. Now, what's really interesting about this slide is the metaphor of the quark to understand Dn. Imagine it acting as a tangible physical stopper against infinite regressing. Think of it almost like a Big Bang stopper, where all the bottle fizz is dynamically compressed right on the other side. This physical boundary is exactly what prevents the mathematical Xeno drift that plagues continuous calculus. It ensures that our computations stay anchored to reality. The source material actually hits the nail on the head with this quote. A D-quarked finite area end is computational, and an infinite vanishing point end is not.
See, mathematical infinity might be a really fun concept for theoretical physics, but down in the hardware, you never actually reach it. In the HU framework, infinity isn't just a bottomless pit. It's physically corked by the substrate noise floor in the Q6464 domain. It forcibly stops the calculation from burning up energy trying to resolve an impossible, endless number. To actually build this structurally, the system uses what's called side A normalization. Typically, you'd fix the radius of a circle to 1, right? But that forces you to use irrational sines and cosines to find points along the curve. This framework flips that. It fixes the transverse component, side A, to unity. By purposefully setting A equal to 1, we literally secure the metabolic ground. We completely bypass the need for pi, or any of those irrational continuous angles.
And that clever trick creates what researchers call the Cayley-Farey Bridge. You can think of it as an incredibly efficient translator. It takes continuous, spinning, rotational space and transforms it into bit-perfect, discrete clicks. Because we're safely anchored to CITA, we map discrete orientation directly onto a rational lattice using integer-only arithmetic. Ultimately, we're trading complex, energy-draining trigonometric approximations for simple, native bit shifts. It's brilliant. When you start addressing surface regions, like physical tiles, rather than just invisible, zero-dimensional points on a grid, a bit-perfect Cartesian diamond horizon reveals itself. The perfect squares align seamlessly along the cardinal axes. The mathematical expansion works flawlessly here, precisely because it's anchored to a fixed physical boundary, not a continuous vanishing point. It proves once and for all that space can be mapped efficiently without ever touching an irrational number. Let's move to the hardware, because this is where the payoff is just insane. Based on 28 nanometer CMOS benchmarks, standard floating point multiplication for attention scores costs about 3.7 picojoules. But when we use that CITA reciprocal shift we just discussed, the energy cost plummets to 0.05 picojoules. We're completely replacing heavy, continuous math with a microscopic metabolic floor. That is our 74x drop in energy requirements. So how is this massive energy savings actually realized in the chips? Through the halting gate revolution. Because the math now has a discrete quark, the hardware can actively track that Dn resolution remainder. And as soon as that remainder hits the threshold, bam, it triggers a deterministic pruning controller. The system actively halts attention heads dynamically the second the floor is hit, which instantly bypasses those high-latency memory loads. The discrete math translates directly into extreme physical energy preservation. Which brings us to the ultimate conclusion here. The Celti's surface establishes a deterministic halting boundary for hardware. By providing a true logarithmic answer to that 400-year Naperian fracture, the HU framework fundamentally rewrites the rules of the game. It stops computational drift in its tracks, it kills thermodynamic waste, and it makes bit-perfect infinite context language model inference a real sustainable reality for the future. So, I want to leave you with this final thought. We've seen how shifting from a continuous, floating approximation to a bit-perfect, fixed mathematical truth drops our energy footprint by 74 times. If mathematical truth is indeed the most metabolically efficient form of representation out there, what infinite spaces will we construct next? Seriously, once we finally stop wasting our energy calculating endless gunk, the possibilities for what we can build are truly boundless. Thanks for joining me on this explainer, and I'll catch you next time.